Hello and welcome to today's class on relativity. We're going to go through chapter 1 today, which is called Departures from Newtonian Mechanics. We're going to watch Newtonian mechanics break. We're going to watch it fall down. We're going to watch it be pushed beyond its domain of validity. We're going to watch it screw up. We're going to see, we're going to turn to nature and ask or see experiments from nature will tell us that there exists an ultimate speed, which it should be no surprise to you is going to be the speed of light in vacuum. We're going to look into the inertia of energy, inertia in the sense of mass, in the sense of inertial mass, in the sense of if something is heavy and you apply a force, the heavier it is, the slower it accelerates. We're going to see a profound connection between inertia, inertial mass, and energy. In fact, we're going to see that in an appropriate system of units, these different concepts are actually the same thing. I'm referring to the most famous equation in all physics, E equals mc squared. Then we'll look at energy, momentum, and mass. And by the way, we're going to be deriving E equals mc squared twice in today's class. If I was to rubbish today's class, I'd say that it's a nice broad brush overview to many of the themes of relativity. But I could rubbish this lecture for two reasons. One is all of the derivations are going to be fairly inelegant compared to when we redo those derivations from a much more elegant perspective later in the course. A second reason for criticising today's class is that the most important part of relativity, which is the word relativity, won't actually enter. So the idea of the relativity concept, which is one of the most powerful, unifying and important ideas in all physics, that relativity concept won't come to the fore until our third class. So having suitably rubbished today's lecture, let's go into the first section, which is called the ultimate speed. So let's consider electrons, and suppose you were to have two plates with some potential difference between them. So this is a positive and negative plate with, let's say, a certain voltage between them. Now suppose that this voltage was, let's say, on the order of 100 volts, and suppose that we were to place an electron at one of the plates. Now this electron will move from low to high potential. This electron, this initially stationary electron, will accelerate from the left plate to the right plate. And the question is, once it strikes the right-hand plate, what velocity v will it have, or what speed v will it have? So we're accelerating an electron from rest between two plates that have 100 volts of potential difference between them. Now this is a trivial calculation which you can do, and what you'll find is that if, unfortunately v for voltage, v for speed, but if you have 100 volts, then this speed, v, let me call it s, the speed s will be on the order of 6,000 kilometres per second. That's fast compared to our everyday intuition, our everyday experience, but it's slow compared to the speed of light. And if you do a calculation based on Newtonian mechanics, it'll give you the right answer to within the accuracy of your experiments. But let's now ask the question, instead of having hundreds of volts of potential difference between the plates, let's instead have millions of volts. Let's have mega electron volts between these plates. If you do a calculation based on Newtonian mechanics, conservation of energy, kinetic energy equals half mv squared, that kind of stuff, you'll get the prediction that the electron, if you have mega electron volts or more between the plates, will travel at faster than the speed of light. That's fair enough, but we can ask the question, what does nature say? Experiment is the ultimate arbiter of physical theories. What does nature say if we do an experiment where we accelerate electrons from rest between plates that have mega electron volts of potential difference between them? So you do the experiment, and you measure a series of speeds, s, or squared speeds, let's call them s squared, and you plot this versus a kinetic energy k, and you just do the experiment. Yep, you do the experiment, and what you see will be the following. You'll get a series of data points, and you'll get a curve like this. Now this is, the actual data is given in figure 2 of the lecture notes. there's a few things to note here. One is that this curve for small kinetic energy K is approximately a straight line. A second thing to note here is that this squared speed asymptotes at c squared, c being the speed of light in vacuum. So this series of crosses, which we can fit this curve to, is what nature tells us. This straight line is what happens if you consider only very small kinetic energies that are much less than a mega electron volt. Just to put a scale on this, this would be about 5 mega electron volts. Yep. So nature is telling us that we get this curve. Again, I mentioned earlier that experiment is the ultimate arbiter of physical theories. Let's consider Newton's theory. Now, one of the most common formulas in Newton's theory is that the kinetic energy of a moving particle, in this case an electron, is related to its mass m, and let me use v again for speed. So speed v as follows. So what this says is that if we were to solve for v squared, because after all here we're plotting v squared versus k, if we were to solve for v squared, you would get v squared equals 2 on m times k. In other words, v squared should be proportional to k. A plot of v squared versus k should be a straight line, which is what you get if you do the experiment, but for low kinetic energies. I want to emphasize that Newton isn't wrong. Like all physical theories, Newtonian mechanics has a domain of validity, and that domain of validity is don't make your kinetic energy of your particle too big, don't make its speed too big. You'll get a straight line, v squared is proportional to k, a straight line of gradient 2 on m. This thing has a gradient 2 on m. Yep. In accord with the Newtonian prediction, but nature tells us that Newton gets it wrong, and progressively more wrong, and progressively profoundly wrong, if the kinetic energy is too large. So if you were to ask me the question, if you ask the question, was Newton wrong? I'd say yes and no. No, because Newton's theory works within its domain of validity, and therefore Newton is not wrong. His theory has limits. Alternatively, if you're trying to look at phenomena where your particles have, or your electrons in this case, have energies of mega electron volts with corresponding speeds, which are a non-negligible fraction of the speed of light, then Newton's going to get it wrong. And this is where the subject of relativity comes in. Relativity is going to change mechanics, but relativity applies to all physics, a point that I won't get to until the third class. So here we have experiment. Here we have Newton breaking down, but we have the question, what physical theory will get it right? What physical theory will predict the correct value or the correct functional form for this curve? Yep. So that's what we want to work towards. So let's now look at Einstein's box. This is a way of using high school mathematics and first year physics to work out the most famous formula in all physics, which is E equals mc squared. And E equals mc squared is about the inertia of energy, the inertial mass m associated with energy E via E equals mc squared. Now Einstein liked thought experiments, also typically known in German as Gedanken experiments. And these are experiments that take place in the mind of the thinker, of the physicist, rather than in a laboratory. And one of Einstein's most famous thought experiments, which talks to the inertia of energy, which will lead us towards E equals mc squared. And this formula, by the way, the most famous formula in all theoretical physics, will derive 3 times in this course, twice today and a third time later. The third one, by the way, will be the most elegant, but also the least satisfying, because it's so elegant you sort of do one line and there it is. It's like, where's the physics? Having said that, we want to derive this 3 times. The first time, we're going to use Einstein's thought experiment, Einstein's Gedanken experiment, to derive this formula which talks to the inertia of energy. By the way, I'm actually going to ultimately argue that this c squared, if you go to a different unit system, doesn't exist. So I want you to look at this formula with new eyes. It's not E equals mc squared. Choose an appropriate unit system where energy and mass have the same units. This says that E equals m. That's a much more profound equation, which makes the key point much clearer. I'll get to that point soon, but I just want you to stare at that with new eyes, ignore the c squared, think E equals m, and I'll explain those comments a bit soon. But before we get ahead of ourselves, we need to derive this thing using this Einstein box. So the way the Einstein box works is you have some box which is floating in interstellar space. And here it is in figure 3. And this box has a mass of m. It's a hollow box with mass of m, yep, capital M. It's going to have a length of L, capital L. And there's going to be a flash bulb at one end of this box. And at some instant of time, this box is floating there in space. At some instant of time, there's going to be a puff of light, which is emitted from the left side of the box. Now, before we go any further, we know that light has momentum. One of the two tails of a comet, for example, is due to the sunlight shining on the comet. Because the sunlight has momentum, it slams into the comet. There's a change in momentum, which implies a force, which accelerates particles from the comet, giving one of the two tails of the comet. Another way that we know that light has momentum is that if you do an experiment with an evacuated glass tube and a little spindle and a series of mirrors, and these mirrors are blackened on one side and silver on the other, you shine light on it and this thing spins. If you get a good one of these, it'll spin anti-clockwise. If this is silvered and you shine the light this way, then the light bounces off the mirror, it imposes a force and it spins the other way. If you get a crap one from a toy shop, it actually spins the wrong way. The reason is that there's not evacuated enough. There's air in here. The other side of the mirror is black. The black bit heats up. It heats up the air, which then expands and pushes it around the wrong way. So a good one of these things will spin. If this is the mirrored side, the light slams into it, bounces off and makes it spin. This, whether you look at the second tail of a comet or a spinning weather vane inside an evacuated glass tube, you'll learn that light has momentum. And the energy E of the light, of the photon, is related to the magnitude of its momentum P as follows. And I'll leave this as an exercise, exercise 2. By the way, the exercises are an intrinsic part of the course. Handwritten solutions to all the exercises are available online. Yep. So we know that momentum is carried by this burst of light. So if momentum is carried by this burst of light, well, we're staring at this box. There's a puff of light created from a flash bulb here. That light carries momentum. If the light carries momentum, then the box must recoil. Just to repeat, if the light carries momentum, the box must recoil. Let's work out the recoil velocity of the box. Well, from momentum conservation, we have E equals PC, which implies that the magnitude of the momentum of the light pulse is related to the energy it carries. So there might be multiple photons. The total energy is capital E. This is the magnitude of the momentum of the light pulse. So by conservation of momentum, let's stick an axis here. This is an intrinsically one-dimensional problem. Let this be the x-axis, the relevant axis, and let this be the momentum in the x direction. Momentum of the light plus momentum of the box, mass of the box, recoil velocity of the box, momentum of the light plus the momentum of the box after the light pulse goes off is the same as the momentum before, which is 0. The box was initially stationary. So this is equation 4. So So if we take this equation here and solve for the recoil velocity of the box, in the x direction you get negative because it recoils to the left, minus E on mc. So this is the recoil velocity of the box. This is good. So this box is going to recoil. So it's going to move to the left. So our box is moving to the left while our pulse of light moves to the right. But eventually, and that box is going to move at a constant velocity v in the negative x direction. But eventually the light slams into the right-hand side of the box. Let this be a black absorbing wall, absorbs the light, and the box is going to come to rest again. And we can ask the question, what is the displacement of the box? What is the displacement delta x? Clearly this will be negative, given that this is a positive x direction. We want to ask the question, what is the displacement of the box delta x? So good question, let's answer it. Again, this is taking us towards, using nothing more than high school mathematics, taking us towards E equals mc squared. The speed equals distance over time, therefore distance, the distance travelled, in this case delta x, is going to be the speed times the time. I'm being a bit loose in flicking from speeds to velocities, but the context will let you know what's going on. So the recoil distance is going to be the recoil velocity multiplied by the time. The recoil velocity is this. What's the time of recoil? Well, time equals distance over speed. So I want to put the recoil time here. Distance equals speed times time. What is the recoil time? Well, light had to travel a distance of approximately L in a time. Light had to travel, speed of light equals distance over time, right? Speed of light, distance over time, hence the time of recoil is L on C. And we can put this together and get minus EL on the mass of the box times C squared. So this is now the displacement of the box. Now we're 2 lines away from, or in essence 2 lines away from getting to E equals mc squared. We look at this figure again. This box was stationary in interstellar space. We had some astronaut, which is you, looking at this stationary box. There's no external forces acting on it. There's no external forces acting on it. When we're getting to the nub of the argument, by the way, and this box has moved a distance delta x in the absence of any external force. Now, if there was no mass associated with the light, if there was no inertia associated with this energy E, then you would have an isolated box in the absence of any external forces being moved a certain distance, and that's unacceptable. What we want, or the way to rescue this, the cleanest way I would argue, and Einstein would argue, to rescue this state of affairs, that the centre of mass can't move in the absence of any external forces. The centre of mass by symmetry begins at the centre of the box. The claim is that the centre of mass doesn't move, but a mass, capital M, has moved to the left. Therefore, a mass, let's call it little m, associated with the light, has moved to the right. Just to repeat, centre of mass can't move in the absence of any external force. Let's have the centre of mass here, which is, let's choose it to be x equals 0. If a mass capital M moves to the left by distance delta x, then a mass little m associated with the light has moved to the right by distance of L in such a way that the centre of mass doesn't move. Now there are some leaps of logic there, which you could, if you think hard about it enough, drive a bulldozer through. Ultimate justification for E equals mc squared is from more refined arguments that you'll get several lectures hence. But I invite you to think about that connected chain of logic. Now you need to dig back to centre of mass formulas from earlier studies. And we ask the question, what is the centre of mass? The centre of mass is going to be the mass of the box has moved a distance of delta x. A mass little m associated with the light has moved a distance of capital L. And here I'm adding the masses. I claim that this is the distance the centre of mass moves. If that point's obscure to you, and it was when I was sitting in your shoes, you need to revise the concept of centre of mass from earlier courses. The claim is that this is the expression for the distance the centre of mass moves, and this is a statement that the centre of mass doesn't move at all. So here we have equation 7. Fair enough. Delta x is minus EL on mc squared. Actually, you're better at arithmetic than I am. I also want to give you the joy of discovering E equals mc squared. What I'd ask you to do is just substitute this into here. And within 2 lines, you'll get the most famous formula in physics. All right, so this is good. This is equation 8. Now, I just want to dwell on this formula a little bit. Einstein considered this the most important result of a general character from special relativity. I've given you the quote in the notes. But listen to this. Before the advent of relativity, physics recognised 2 conservation laws of fundamental importance: conservation of energy and conservation of mass. He speaks of this. These 2 fundamental laws, conservation of energy and mass, appeared to be quite independent, but by means of the theory of relativity, they have been united into one law. So what he's talking about here is the meaning of this equation. What this equation does not mean is that energy can be converted into mass and conversely. That's what you'll hear said often, but it's not strictly speaking correct, and it's not radical enough. Because if I was to say energy can be converted into mass, and the standard argument is give me a little mass, I don't know, a gram, c squared is huge, hence there'll be a huge amount of energy in joules associated with a tiny mass. Energy can be converted into mass. A nuclear bomb goes off, and the mass of the fragments, when brought to rest, is less than you began with, hence energy is converted into mass. Again, that's wrong. The reason it's wrong is because this says that energy and mass are the same thing. The system of units that we work in is arbitrary. A second is roughly the time it takes your heart to go from one beat to another. A metre is, give or take, the height of a human, or the height of a human is a single-digit number times metres, right? Kilograms are masses that we can directly apprehend. We choose our units of mass, length, time to be convenient for us, things that we can directly apprehend. Seconds, a metre per second is roughly a footstep per heartbeat. We choose a system of units to be things that we can directly apprehend. Our heights are on the order of a metre. Our time between heartbeats is on the order of a second. Okay, we don't weigh on the order of a kilogram, but a kilogram is a mass that we can directly apprehend. Systems of units are arbitrary. That goes for mass, that goes for length, that goes for time, it goes for speeds, it also goes for energies. So, c squared is a constant. Let's choose a system of units in which the speed of light is 1. You can do that if you want. It might sound a bit crazy, but this is a constant. Why not choose all speeds to be some fraction of the speed of light? Instead of choosing all speeds to be some fraction of a footstep per heartbeat, which is very anthropomorphic, very tied to us as physical beings, why not choose a fundamental speed, which instead of being related to a comfortable walking pace, is actually related to a fundamental speed, the speed of light? Measure all speeds relative to light. So speed of a half is half the speed of light. Speeds here, by the way, have no dimensions. Speed of 0.5 is 50% of the speed of light. Not metres per second, not furlongs per hour, but 0.5, half the speed of light, dimensionless. In such a system of units, which is called natural units, I won't talk about natural units anymore for this course, but our more advanced courses often work in so-called natural units, where speeds are measured as a fraction of the speed of light. This equation then becomes E equals m. In such a system of units, energy and mass have the same units, which is typically mega electron volts. And this makes the point that Einstein's emphasising. Energy and mass are the same thing. So if I have a can of lemonade which is cold, if I heat it up, it has more energy, therefore it has more mass, because energy is mass. If I have a nuclear bomb and I have what's it called? Plutonium nucleus. Here's a plutonium nucleus which has a certain mass, and it fragments into barium and krypton, which flies apart. Energy is mass. The barium and krypton nucleus, sure, if I bring them to rest, their masses added together are less than the mass of the original nucleus, which fissioned. But energy is mass. Moving things have more energy and therefore have more mass than stationary things. So if I have the nucleus, which is about to fission, which has a given mass, it breaks apart into two moving fragments. The energy is mass. The moving fragments are going to be heavier than the stationary fragments. The mass of the original nucleus, stationary relative to U, is the same as the mass of the two moving fragments. Energy is mass. When the sun radiates energy into space, it loses a certain amount of mass per unit time, which is actually 4.5 million tonnes per second. You'll calculate that in an exercise. Energy is mass, right? So the sun is losing 4.5 million kilograms per second of mass. It's losing 4.5 million kilograms per second of energy, and that's being radiated into 4.5 million kilograms of light that gets emitted from the sun per second. Again, this idea of energy being mass rather than energy and mass being interconverted. And again, this is a very, very strong statement. Conservation of energy and conservation of mass actually become the same thing in relativity, because energy is mass. Again, to quote Einstein, by means of the theory of relativity, they, in other words, the law of conservation of energy and mass, have been unified into one law. There's a feat of extrapolation here. I've pointed out you can drive a bulldozer through this argument. One thing that I've done is to implicitly assume that this result, which was associated with a light puff in the context of the Einstein box, is to assume that this is applicable to all physical phenomena. That is a very, very bold assumption. That was Einstein's assumption. It's consistent with the experiment. And so when I extrapolate this from light puffs to fissioning nuclei and cans of lemonade, that is an extrapolation, which is ultimately warranted by its leading to predictions that are consistent with the experiment. That's all I wanted to say about Einstein's box and the inertia of energy. The third and final thing I wanted to say from the top left board is about energy, momentum and mass. Again, without wanting to bag my own lecture, the derivation I'm about to give you is quite inelegant. We'll do it nicely later, but it brings some results to us quickly, which are important, relating energy, momentum and mass. It actually, by the way, is the generalisation of this formula here. So if you take equations 3 and 8, so equation 3 up here, and equation 8 down here, with the C present, and you eliminate E, you'll get equation 9, which says the momentum, this is still of a light pulse, is related to its mass, little m, and the speed of light as follows. Now this looks like a special case of Newton's formula, momentum equals mass times velocity, applied to a light particle. Again, the assumptions come thick and fast, but I want to make the point that a few lectures hence we'll actually state some axioms of special relativity and derive essentially the entirety of the course as logical consequences of the axioms of special relativity. So special relativity, unlike subjects, for example, such as quantum mechanics, can actually be quite cleanly derived from a very small number of axioms. We're working towards that, elegance. It's one of the very few subjects in physics that has that level of elegance that begins to approach that of that beautiful subject, pure mathematics. Most other physics is much uglier and more ad hoc, such as quantum mechanics, much as I love the subject. So all that is by way of apology for the string of assumptions I'm about to introduce. So this applied to light, momentum equals mass times velocity. So it appears to be a special case of the Newtonian formula. Now we're moving from light to any particle. When light had speed c, its momentum was mc. When a particle has mass v, let's assume that Newton is correct. But we can actually see that this m, we now look at this with suspicion, right? Because energy is mass, therefore moving particles are heavier than stationary particles. Moving particle has more energy. If it has more energy, it has more mass. Mass is a function of velocity. So even though the notation doesn't show this, this m is going to be a function of speed. So we want to assume the universality of 8, E equals mc squared. So let's now eliminate m from both 8 and 10. We want to eliminate m from both 8 and 10, and what you'll get will be equation 11. Again, we're working towards this energy, momentum, mass formula. The form that's going to be more useful for us today will be V equals P squared over E. Sorry. V equals PC squared over E. Now I want to put this to one side for the moment. And let's assume we have our x-axis once again. We're going to have some particle, which is going to be in general moving, but only in the x direction. We want to apply a force to it, a constant force F. And when we apply this force for an infinitesimal time, it's going to move through some infinitesimal displacement, delta x. So we can ask the question, what is the increment dE, the infinitesimal increment dE of the kinetic energy of the particle? Well, work equals force times displacement. That work is going to go into increasing the kinetic energy of the particle. That increase could be negative. Work, which is the increment of kinetic energy, will be the force times the displacement, and the displacement is dx. But force is time rate of change of momentum. Now I'm going to do something that mathematicians would shoot me for quite rightly. I'm going to shift this to t under here. If you want to do this properly, you would say, okay, before you get dp dt, it's the limit as delta t approaches 0 of delta p over delta t. Before you take the infinitesimals, this is actually a fraction. So don't take infinitesimals yet, treat this as a fraction and shove the delta t under here, then take the limit. But what you're going to get is this. Yep. But dx dt is the same thing as v. Yep. So we've got equation 12, dE equals v dp. Equation 12, dE equals v dp. But v from equation 11, v dp is the same thing as pc squared on e dp. Fair enough. We can now rearrange this trivially to get e dE equals pc squared dp. This is equation 13. Now I'm going to integrate both sides of this equation, integrate both sides. So integral of e dE will be half e squared plus some constant. Integral of pc squared dp will be half, basically the p becomes a half p squared, c squared plus some constant. Now I've mentioned two constants of integration. I'm going to absorb both of those constants of integration into alpha, which is going to be some real number yet to be determined. Now the context here is we're doing relativistic calculations, but as I often say, new theories should reduce to the old in the domain of validity of the latter. Sure, Newton can break down, but in regions where Newton is correct, we want a more general theory. We want Newtonian mechanics that works for all kinetic energies. If this is Newtonian mechanics, it's still got to give results that are consistent with Newton if kinetic energies are small. So even if we come up with some fancy relativistic mechanics, it's still got to be consistent with Newtonian mechanics in the limit of small velocities. So this looks utterly unlike corresponding Newtonian formula. E equals p squared on 2m for the kinetic energy of a particle. That's what Newton would say is a relationship between energy, momentum and mass in free space. E equals p squared on 2m. This looks nothing like it, but it must reduce to Newton in the appropriate limit. That's a philosophical point. Special relativity, SR, must reduce to Newtonian mechanics NM in the domain of validity of the latter. So phenomena such as X and Y are explained by relativity, but not by Newton. But phenomena such as Z inside this blue circle, phenomena such as Z, for which Newtonian mechanics is fine, but that Z is inside the special relativity circle, so we must have Newtonian mechanics as a limit case of Einsteinian mechanics. That's a philosophical point. It's a point which constrains new, more general theories which claim to cover a broader range of phenomena. It also helps us calculate, here's an unknown constant, I don't know what it is. I'm going to demand that it have a value that be consistent with Newtonian limit when speeds are small. So how are we going to calculate this alpha? We're going to demand that our theory reduce to Newtons. So let's be explicit. Again, I'm going to leave some algebra to you. I want you to eliminate P, the momentum P, from equations 11 and 14. So equation 11 up here, which has a P in it, and equation 14 that has a P in it. I want you to eliminate P and solve for E. If you eliminate P and solve for E, you'll get equation 15. E equals, here's our still mysterious constant alpha, and v squared on c squared. A very, very common thing that appears in special relativity is 1 over the square root of 1 minus v squared on c squared. Now we want to take the Newtonian limit, the non-relativistic limit of this expression. And so let's do it. We've got root 2 alpha. I'm going to write this denominator as something to the power of minus a half. Now I want to make the Newtonian approximation, the non-relativistic approximation. So if my speed v is much smaller than the speed of light, then this thing here will be tiny. This thing will be small in magnitude compared to unity. And this is where our binomial approximation comes in. And that's written explicitly in equation 16, which I'll just remind you. If you have 1 plus theta to some power a, and theta has a magnitude that's much smaller than unity, then we can apply the so-called binomial approximation, so-called because it's the first 2 terms in a binomial series. We can think of this a as a frog that hops in front of the quantity theta that's small. So this is the binomial approximation, which I want to use now. This thing is small, this is theta, this is the frog. It's going to hop in front of the v squared on c squared. And what we'll learn we'll get to equation 17, but the energy of the particle is approximately, again we're assuming that v is much less than c, hence this is much smaller than 1. We've got our root 2 alpha. got 1, the minus and the minus give a plus, v squared on 2c squared. And I can expand this into two terms, which is root 2 alpha plus. Now I want to write the next term in a suggestive way. It's half times something times v squared. Yep. And that something happens to be root 2 alpha on c squared. Because I want Newton to come out of this. And apart from this pesky additive constant, I want half mv squared. I want this to be the mass of the particle. But I need to be a bit careful. So I demand it be so. Choose alpha to be such that this is the mass of the particle, because then, in the non-relativistic limit, the energy of the particle up to some pesky additive constant, which we can throw away because all energies are only measured up to some relative additive constant, this must be the mass, and hence we can deduce alpha. But mass is a function of velocity. So what is mass? Well, mass is a function of velocity. It's actually a relative term. You say that this chalk is moving. I have to introduce relativity briefly. You say this chalk is moving, therefore it's heavier than when the chalk is stationary. But relative to me, that chalk is stationary. So I'd say that this chalk has a smaller mass than you'd say, because you say the chalk is moving and I say it's stationary. So mass is a relative concept. The concept of the mass doesn't exist in any absolute term. We want this to be mass, which when the object is stationary, which we call rest mass. The mass that the object has relative to some observer when that mass is stationary. So this is the rest mass of the particle. So if we demand that this thing here be the rest mass, you'll get equation 18, which lets you work out what alpha is. It's half the rest mass squared times c to the power of 4. So we've done something quite profound here. We've used the demand that the new theory, the higher theory, should reduce to the lower theory, the less general theory, in the domain of validity of the latter, to work out this constant. So with all this, we could look at this expression here and say, good, energy is root 2 alpha, which will be m naught c squared, plus half m v squared. Again, this is not a general formula, but the formula that corresponds to the non-relativistic limit. Now, I haven't mentioned the following point in the notes. From a Newtonian perspective, this is a meaningless additive constant. From an Einsteinian perspective, here's my stationary bit of chalk with a given rest mass, little m naught. Einstein says this has a huge amount of energy, E equals mc squared, or E equals m naught c squared. If we now allow that chalk to move at a non-relativistic speed, its energy will have two parts. Newton says this is a relative additive constant, but this is actually the rest energy of the big piece of chalk, plus a little bit, and that extra little bit is half mv squared, if you're non-relativistic. Even though this alpha was deduced under the non-relativistic limit, this is a relationship amongst constants, hence it must be true in general. So now that we have alpha, we can substitute it into equations such as 15 and 14. We can substitute this expression for alpha into equations 14 and 15, which are more generally valid. That I don't make this assumption here. So when you do precisely that, when you put the expression for alpha into equation 14, you'll get the answer to section 3. You'll get the relativistic energy momentum mass relationship. Now, I'd argue that the two equations in boxes are the most important equations in this lecture. If you asked me to pick one, I'd actually say that this was the more important. The reason is E equals mc squared is actually a special case of this. If we're talking about an object at rest, m equals naught, this disappears. You've got E squared equals m naught squared c to the fourth, which is E equals m naught c squared for a particle at rest. Now this is actually more general, sorry, because this can be a moving mass. So I like both these formulas equally, let me say. Yeah, I'll take that back. I love them both equally. And these are the culminations of today's lecture. Now I want to beat a path back to this graph here. If we substitute the expression for alpha from 18 into 15, we'll get, I'm leaving a judicious gap here, we'll get E equals m naught c squared over the following. Fair enough. That's this formula with alpha given by this thing. But E equals mc squared, if the object is moving or not, it's going to have a mass m c squared, such that mc squared is its energy. So these formulas are actually consistent. We just need to be careful that this is a moving mass. A mass is a function of velocity. So let's get rid of the c squared, and you get this formula here, which is equation 21. This is the mass as a function of velocity, and this quantifies what I said earlier. The faster something moves, the heavier it gets, because energy is mass. If v is 0, the moving mass is a rest mass. If v is greater than 0, but less than the speed of light, the moving mass will be greater than the rest mass. By the way, if you have a physical theory where v can be greater than the speed of light, the mass actually becomes purely imaginary. There are such theories. That's the theory of tachyons. Very much worth checking out if you're interested. So here we have equation 21 for the moving mass, being proportional to the rest mass, but also growing with increasing speed. If you were to plot this thing, moving mass as a function of velocity versus velocity, you would get something that asymptotes at the rest mass, m naught, but actually diverges. Finally, kinetic energy. Now, kinetic energy, called K, is one of the most primary concepts in Newtonian mechanics. It's very, very rarely used in relativity. In fact, I believe this is the only time I'll use kinetic energy in the entirety of the course. What is kinetic energy? From a Newtonian perspective, from an Einsteinian perspective, this has a huge rest energy. If I make it move, it has a little bit more energy, a tiny bit more energy, half mv squared gets added to the rest energy. So what is the kinetic energy? It's not the energy anymore. This is a particle moving in the absence of a potential, but kinetic energy is not the energy. It's actually the energy minus the rest energy. So this is equation 22. Yep. But the energy, if I put a c squared back here, energy is m naught c squared divided by this square root. M naught c squared divided by that square root. I'll factor this out because I'm going to have a minus 1 here. So this is actually an expression for the kinetic energy as given in equation 22. Now if you want to, you can solve this for v squared as a function of k. I invite you to do this. Solve this expression for v squared as a function of k. You'll get a formula which is exactly this curve here that's consistent with experiment. That's it for today. Thank you. I'll see you in the tutorial this afternoon.